Hi, welcome back to educator.com. Today we're going to talk about inverse functions. A function does a transformation on an input. We've talked about functions for a while now, but what if there was some way to reverse that transformation? This is the idea behind an inverse function. It's a way to reverse a transformation, reverse the process that another function is doing. It's a way to get back to our original input. By way of analogy, let's imagine a factory where if you give them a pile of parts, they'll make you a car. Now, if you take that car down the road to this other factory, you can give them that car and they'll give you back the original pile of parts you started with. So there's one factory where they make cars out of parts, but then there's a second factory where they take cars and break them down into the original parts that was used to make them. So there's one process, but there's also an inverse process that gets you back to where you started. If you follow one process with the other immediately, it winds up as if you haven't done anything, right? If you bring it the pile of parts to the first factory and then take that car to the second factory and they give you back the pile of parts, it's like you just started with a pile of parts and didn't do anything to it. So this is the idea behind an inverse function. It reverses a process. It reverses a transformation, gets you back to where you started. We've used the analogy of a function as a machine before, and it's a good image for being able to get across what's going on with inverse functions as well. So a function machine, it takes inputs and it transforms them to outputs by some rule. So what we're used to, we plug in x into the function f and it spits out f acting on x, f of x. Now we could plug it into another one. We could plug it into an inverse machine, an inverse to f, and that would be called f inverse. The f with the little -1 in the corner, f with the -1 in the upper right corner, denotes the inverse of f. We call it f inverse. So if we plug f of x into f inverse, into that machine, we get right back to our original x, as if we hadn't done anything. So the first machine does something, but then the second machine reverses that process, gets us back to where we started. So is there a requirement for reversing? Can we make an inverse out of all functions out there? No. Why? Let's see why by analogy first. Imagine a factory where if you give them a pile of wood or a pile of metal, they give you a basketball in return. The basketball is the exact same whether you started with wood or metal. It's always the exact same basketball. It doesn't matter what you gave them, it's just basketball. Now, let's say you walk down the road to another factory, you give them that basketball, you tell them to reverse the process, and then you walk away. You give them no other information. Can that factory take basketball and transform it back into pile of wood or pile of metal if all they have is basketball and no other information? No, they have no idea what you started with, right? Maybe they've got wood, maybe they've got metal, but the point is they have no way to be able to know which one they're supposed to give you at this point. They don't have the information. The only person who has the information is you when you brought the original wood pile or brought the original metal pile. Because all they've got is the basketball, and the basketball could indicate wood or it could indicate metal. They have no way to know what you started with. There's no way to figure out. The information about what you originally had has been destroyed, although you would know it because you brought it to the factory. But assuming you forgot, then the information has been destroyed. No one has the information anymore. Another way to think about it would be if you took a piece of paper and you burned that piece of paper, you'd be left with a pile of ashes. Now someone could come along and go, oh, pile of ashes, it used to be a piece of paper. But if you take two pieces of paper and you write two completely different things on the two pieces of paper, and then you burn the two of them, a person could come along and go, two piles of ashes, and they know it was paper, but they wouldn't know what was written on them. They wouldn't be able to get that information back. The information has been destroyed. They know it was paper, but they don't know what was written on the paper. The basketball one, you've given them wood, you've given them metal, you get the same thing. The information about what you started with has been lost. The information has been destroyed unless you come along and also say, oh, by the way, that basketball came from blank. The issue in this scenario is that we've got two inputs providing the same output. Whether it's metal, whether it's wood, you get basketball. So if we try to have a reverse on that, we have no way to know which one to go back to. We don't know if we're going to go back to metal, we don't know if we're going to go back to wood, because we don't know what basketball is representing. So to be a reversible process, for it to be possible to reverse something, the process has to have a different output for every input, right? You have to give them, if you give them metal, they have to give you one color of basketball, and if you give them wood, they give you a totally different color of basketball. Then the second factor would go, oh, that's a wood basketball, or oh, that's a metal basketball, and they'd be able to know what to do at that point. So for a function f to have an inverse, It has to be that for any a, b in the domain, any a or b that we could use in f normally, where a is not the same thing as b, where a and b are distinct from each other, they're different, then f of a is different than f of b. F of a does not equal f of b. So if a and b are different, then the function's outputs on a and b are different as well. So different inputs going into a function have to produce different outputs. We call this property one-to-one. If this function has a property where whatever you put in, as long as it's different from something else going in, means that the two things will be different, that's called one-to-one. Different inputs produce different outputs, right? You give them metal, you get one color of basketball. You give them wood, you get a different color of basketball. Here's some examples so we can see this in a diagram. Here's an example that's one-to-one. A goes to 2, B goes to 1, C goes to 3. They each go to different things. Different inputs each have different places that they wind up going. Something that's not one-to-one, A goes to 1 and B goes to 1. It doesn't matter that C goes to 3 because A and B have both gone to the same thing, so they have different inputs that are producing the exact same output. A and B are different things, but they both produce a 1, so it's not one-to-one. We've got that copy. We're putting in wood and putting in metal, and we get basketball in both cases. And then finally, just to remind us, this one over here, hopefully you remember this, is not a function. And it's not a function because B is able to produce 2 outputs at once, and that's something that's not allowed for a function. If a function takes in 1 input, it's only allowed to produce 1 output. It can't produce multiple outputs from a single input. So why do we call it one-to-one? Why are we using this word one-to-one? Well, we can think of it as because A has 1 partner, and B has 1 partner, and C has 1 partner. Everybody gets a partner, and nobody has shared partners. Everybody gets their partner, and that partner is theirs. They don't have to share it with anybody else. So it's 1-to-1. This thing is matched to this thing, and there's nobody else who's going to match up to that one. 1-to-1. All right. How can we test for this? One way to test for this, to test if a function is one-to-one, we know if we're going to be one-to-one, that every input must have a unique output, right? That was what it meant to be one-to-one. If we have different inputs, we've got different outputs. So if we draw a horizontal line on the graph, it can intersect the graph only once, or not at all. Remember, a graph, if we've got some picture on a graph, like if we've got this point, then what that means is this is the input, and this over here is the output, right? We make it a point, input, comma, output. That's why it's x, comma, f of x. If it's f of x equals x squared, then we plug in 3, and we get 3, comma, 9. 3, comma, 3 squared. The input is our horizontal location. The output is our vertical location. So the horizontal line test is a way to test if the function has multiple outputs, has the same output for multiple inputs. We draw a horizontal line across because wherever an output hits the graph, we know that there must be an input directly below it. If a function is not one-to-one, you'll be able to draw a horizontal line that will intersect it twice, or maybe even more. Let's look at some examples. So first, here's one that is one-to-one, because whenever we draw any sort of horizontal line, it's only going to cut it once. The only place that might seem a little confusing is if we draw near here. It might be like, well, doesn't it look like those are some stacked? Well, remember, this is just, we can't draw perfectly what's being represented by the mathematics. We have to give our lines some thickness. In reality, the line is infinitely thin, so while it looks like they're kind of getting stacked, it's actually still moving through that zone. It's not constant. It's increasing just a little bit, but it isn't constant. Let's look at one that's not one-to-one. Over here, this horizontal line, or many horizontal lines that we could make, it cuts at 2 places. So we know here and here there are 2 inputs. We can produce the same output from 2 different locations. So we've got 2 inputs making 1 output. So that means we're not one-to-one because this guy has partnered to that height, but this guy has also partnered to this height. So we're not one-to-one because we've got to share an output. Now that we've got all these ideas in mind, we're finally ready to define an inverse function. We can really talk about them and sink our teeth into it. Given some function f that is one-to-one, has to be one-to-one for this to happen, there exists an inverse function, which we denote as f with a -1 in the top right corner, such that for all x in the domain of f, any x that could normally go into f, any value that could normally be input, f inverse acting on f of x becomes just x. So we have f acts on x like normal, and then f inverse acts on that whole thing, and it sort of breaks the action that was done by f and returns us back to our original input. In other words, when f inverse operates on the output of f, it gives the original input that went into f. Caution, I want to warn you about something. F, with that -1 on the top right, it means the inverse of f, not 1 over f. This can be confusing because if you've taken algebra and remember your exponents, you might have forgotten them, but we'll talk about them later in this course. -1 can mean a reciprocal for numbers. So 7 to the -1 becomes 1/7. X to the -1 becomes 1 over x. But f is not to the -1. It's just a symbol that says inverse. Hey, this is a function inverse. So in general, for the most part, f -1, f inverse, is not the same thing as 1 over f. The inverse of f is normally not the reciprocal of f, the 1 over f. This is not the case, so this exponent business where 7 to the -1 is 1/7, that's not the case for functions. On a function, the -1 does not represent an exponent. It is not an exponent, but it instead tells us function inverse. It's a way of saying this is an inverse function. That's what it's telling us, not flip it to the reciprocal. How can we get domain and range for f inverse? We can figure these out by looking at f. So remember, the set of all outputs from f is the range for, so the set of all outputs for f is its range. The things that x can get mapped to by f. What f is able to map x to is the range of f. So domain of f is everything that x can be, everything that we can plug into f. And then the range of f is everything that can come out of f. Now f inverse has to be able to take any output of f, right? It's not very good at reversing if there's some numbers that it's not allowed to reverse. So it has to be able to reverse anything from f. So if it's able to reverse anything from f, then that means the range of f has to be everything that we can put into f inverse. So the domain of f inverse, the things we can put into f inverse, is the range of f. The domain of f inverse is the range of f. Likewise, because f inverse then breaks that f of x and turns it back into original inputs, so we must be able to turn it back into all of the original inputs because all of the original outputs have to be over here. So anything that we can make it to, we have to be able to make it back from. So since we're able to get back everywhere, that means that we can output all the possible inputs for f. So since we can output all the possible inputs, because we can reverse any of the processes, then it must mean that we are able to get the range of f inverse from the domain of f. So the domain of f tells us the range of f inverse, what we're allowed to output with f inverse, and the domain of f inverse tells us the range of f. So domain of f inverse is the things that f is able to output, and the range of f inverse, the things that f inverse is able to output, is what we can put into f, the domain of f. This idea is going to let us prove something down the road. Now we can get to that proof. Inverse of an inverse. What is the inverse of an inverse? In symbols, what is f inverse inverse, right? What do we do if we're going to take the inverse of something that's already doing inverses? Now, it might seem a little surprising, but it turns out that the inverse of f inverse is just f. So the inverse of f inverse is f. Now, it seems a little surprising maybe, but it makes a sort of intuitive sense, right? If you do the opposite of an opposite, you get to the original thing. If you do an action, but then you're going to do the opposite of that action, but then you do the opposite of that action, then you must be back at your original action. So we might be able to believe this on an intuitive level. It makes sense intuitively that two opposites gets us back to where we started, but let's see a proof of this fact formally. Let's see it in formal mathematics. So how do we get this started? Well, by definition, f inverse is the function where, for any x, f inverse acting on f of x is going to just give us our original x, right? If f acts on an input and then f inverse comes and acts on that, we get back to our original input. Now, consider f inverse inverse. By this definition of the way inverses work, it must be that f inverse inverse, when it acts on the thing that it's an inverse of, right? F inverse inverse is an inverse of f inverse. I know, it's complicated to say, but this guy right here is going to be the opposite action of f inverse. So if we take any y, don't get too worried about x and y. Remember, they're just placeholders for inputs. So similarly, for any y, f inverse inverse acting on f inverse of y is going to just get us right back to our original y. It's the same structure as what's going on here with f inverse f of x equals x, is we're just reversing a process. So it doesn't matter that one of the processes is already a reverse process, because we're reversing this other reverse process, so we get back to our original thing. Now, we know that y is in the domain of f inverse because we're allowed to put it into f inverse, right? It's allowed to go into f inverse. Now, we know from our thing that we were just talking about that the domain of f inverse is the range of f. So there has to be, if f inverse is the range of f, right? Domain of f is the range, the domain of f inverse is the range of f. Now, if you're in the range, then that means that there's some guy out there that can produce this. So that means that if you're in the range of f, there must be some x in the domain of f, right? There has to be some way to get to that place in the range so that f of x is equal to y. So there's some x out there in the domain of our original f that f of x is equal to y. So now we've got what we need. We can use this f of x equals y, and we can just plug it in right here and here. We'll plug it in for the two y's up here, and we'll see what happens. Thus, f inverse inverse acting on f inverse of f of x, because remember, we know that there has to be some way to get an x such that f of x equals y because of this business about domain and range. So we plug that in here, and we plug that in here, and we've got f inverse inverse on f inverse of f of x must be equal to over here on the right as well, right? We're just doing substitution. But we know by the definition of f inverse on f of x that this just turns out to be x. So this whole thing right here just boils down to x, simplifies right out to x. So it must be the case that f inverse inverse of x is the same thing as f of x. So if f of x is the exact same thing as f inverse inverse of x, it must be the case that f inverse inverse is just the same thing as f. And boom, our proof is finished. Great. How can we interpret this graphically? There's a great way to interpret inverses through graphs. First off, let's consider f of x equals x cubed plus 1. Now, we know this one has got to be 1 to 1 because it passes the horizontal line test, right? If we come along and try to cut this with any horizontal line, they're only going to be able to cut in one place. Even here where we sort of seem to flatten out, it's still moving because we know it's x cubed plus 1, and it never actually stops going up. It just slows down how fast it's going up, and our lines have to have thickness, so while it kind of looks like they're stacked, they're not really. So we see that it passed the horizontal line test, so it must be 1 to 1. If it's 1 to 1, we know it has to have an inverse. That's how we talked about this right from the beginning. Now notice that the graph, any graph, is made up of the points x, comma, f of x. We talked about this before, right? 0 gets mapped to 1 when we plug it in as f of 0 equals 1, so that gives us the point 0, comma 1. That's how we make up our original graph for f. Now the graph of f inverse will swap these coordinates, right? It takes in outputs and spits out inputs in a way. So its input will swap these two things. It takes in f of x and it spits out x. So the points of f inverse will be the reverse of what we had for the points of the other one. So f of x comma x is what we get for f inverse. Now visually what that means is that f inverse is going to be the mirror of y equals x, and that's our line right here, y equals x. So why is that the case? Well, look, we swap x and y coordinates if we go across this because -3, comma 0 swaps to 0, comma -3 if we're going over y equals x, right? If we're mirroring across this, we will swap the locations, and so if we mirror over y equals x, we are going to swap x and y, y and x. We will swap the order of our points because y equals x is sort of a way of saying, hey, let's pretend for today that I'm you and you're me, right? Y is going to pretend that it's x and x is going to pretend that it's y. They're sort of swapping places when we do a mirror over it. So that means our picture, mirroring f over y equals x, we get the graph of f inverse, right? So we look at this, we mirror over it, and we get places like this, right? We see how we're just sort of bouncing across it. And this is going to happen with any of our inverses graphically. So anytime f inverse is being looked at, we know it's going to be a bounce, a reflection through, a mirror over. It's going to be symmetric to f with respect to the line y equals x. Since f inverse is swapping outputs and inputs, right? It swaps outputs and inputs. It's going to be sort of reversing the placements of these. So the graph of f inverse will always be symmetric to f with respect to the line y equals x. We'll bounce across, because when you bounce across y equals x, you swap your coordinates. Now, there's many ways to say this. I'm saying bounce across. That's not really formal, but we can formally say it is symmetric to f with respect to the line y equals x. You could also say it reflects through y equals x, or it reflects over y equals x. You could also say it mirrors over, or it mirrors through y equals x. There's many ways to say it, but the same things. All the idea is that we're going to bounce across, and that point will now show up at that same distance here. So let's see what it looks like. We bring them in, and indeed, they pop into those places. They pop into being a nice symmetric to the line y equals x, and that makes sense. We've replaced inputs with outputs, outputs with inputs. They've swapped locations, right? We look at this one here, and the point 3, 0 on the inverse is connected to 0, 3 on the original function. Same sort of thing on both of them. All right, so we've talked a lot about what's going on. We've got a really great understanding of the mechanics behind an inverse, but how do we actually find an inverse? So now that we understand them, we're ready to actually go and find them. How do we turn an algebraic function like f of x equals x cubed plus 1 into a formula? So before we do this, a formula for f inverse, before we do this, consider that f inverse is taking the output of fx and it's transforming that into x. So to find a formula for f inverse, we want a formula that gives x if we know f of x. So normally, f of x equals x cubed plus 1, for example. Normally, we have x. We know x, and from that, we get our f of x, right? You plug in an x into a function, and it spits out f of x. So f inverse is sort of the reverse of that. We know f of x, and we want to get x out of it. So to be able to do this, we're solving f of x equals x cubed plus 1 in reverse, right? F of x equals x cubed plus 1. Well, we move that over, f of x minus 1 equals x cubed. So now we've got cube root of f of x minus 1 equals x. So if we know what f of x is, we can figure out, hey, that's what the original x that did it. We're solving it in reverse. We've reversed the function, right? As opposed to solving f of x in terms of x, we're solving x in terms of f of x. Now, this is a little bit of a confusing idea. So instead, I'm going to show you a method to do this. So the idea of reversing is really what's behind finding inverses. It can be a little hard to understand what to do on a step-by-step basis. We're normally used to solving for f of x in terms of x, right? Having f of x just on its lonesome on one side and having a bunch of stuff involving x on the other side. So at this point, it might be a little bit confusing for you to try to do it the other way. And it would work, but let's learn a method that makes some of that confusion go away, do stuff we're more used to doing. So here's one step-by-step guide for finding inverse functions. Very first thing we have to do, we have to check that the function is 1-to-1. It has to be 1-to-1 for us to be able to find an inverse at all. Now, f of x equals x cubed plus 1, we just saw its graph. Remember, it looked something like this. So we already know passes the horizontal line test, does a great job, it's a great function. So it is 1-to-1. Great. We've already passed that part for this. Next, we swap f of x for y. This is going to be a little bit easier for us in solving. We're used to solving for y's. We're not really used to solving for f of x's, so this will make it a little bit less confusing. So we switch out f of x for y. Great. Next step, we interchange the x and the y. So in this one, we've got x in its normal place, y in its normal place. What we do on step 3 is we swap their places. Y takes the place of all of the x's, and x takes the place of y. So we swap x and y, interchange x and y. So every time you had an x in step 2, you're now going to have a y. Every time you had a y, which is probably just the one time since it was from a function, you're going to now have an x. So that's how we're doing an inverse. This step, it's the reversing step. Solve for y. So at this point, we've got x equals y cubed plus 1. So if x equals y cubed plus 1, we solve for it. We just move that 1 over, x minus 1 equals y cubed. And we've got cube root of x minus 1 equals y. And you'll notice that this actually looks pretty much the exact same as what we just did on the previous slide, but perhaps a little less confusing because it's what we're used to seeing. So we've got y equals cube root of x minus 1. And finally, we replace, just like we replaced f of x with y, we now do a reverse replacement, but we are now going to f inverse. So y now becomes f inverse of x. So f inverse of x is equal to cube root of x minus 1. F inverse of input equals cube root of input minus 1. Great. Now, while this method will produce the inverse if followed correctly, it is not perfect. Now remember steps number 2 and number 3. In that we had the swap f of x for y, and then we were told to interchange x and y. Remember, they swapped places. Now, notice these equations are completely different. They are totally different from one another. Yet they're still using the same x and y, right? They're using the same x and y. Technically, it's not possible to have both of these equations be true with the same x and y. X and y can't possibly fulfill both of these equations at the same time because they are completely different equations. So what's going on here? When we swap in step number 3, we're really creating a new different y. When we have swap f of x for y, it's really like red y or something here. But then, when we do the interchange, it becomes a totally different color y. It becomes like blue y here. So we're creating a new different y. The y, when we first swap, is different than the meaning of the second y. The swapping y is a different y from our first time that we replaced f of x. So the first one is standing in for f of x. That was our red y. And then the second one stands in for f inverse of x. That's really taking the place there. This implicit difference between y's can be confusing, so be careful. I'd recommend make a note on your paper. Make a note when you're working that says where you swap. So use a note to see that swap of x and y so that you can see the switch over to this inverse world where you're now in inverse world and you can solve for an answer. This is a bit confusing. So why are we learning this method if it has this hidden, confusing, implicit difference when we sort of really think about what's going on? In short, the reason we're doing this is because everybody else does. It's not because it's perfect. It's because everyone else out there pretty much learns this method for solving inverses, for finding inverses. Most textbooks and almost all the teachers out there teach this method, so it's important to learn not because it's absolutely perfectly correct, but because it's standard, so that you can talk to other people and talk about inverses, and they will understand what you're talking about because they're doing the same method that you're doing. If you do something different, they might get confused. If they're really clever or they really understand what's going on, they'll be like, oh yeah, that makes perfect sense, but we want to go with sort of the standard method so that other people will understand what we're doing. And, if we're taking a course at the same time as we're watching this course, the teacher will go, oh, that's correct, as opposed to being confused by what you're doing and marking your grade down. But the important idea here, the really important idea inside of this thing that's confusing is the reversal. That's what the moment that's all about, is that moment between number 2 and number 3, the number 3 step where we reverse and we create this new y. We reverse the places. We're solving, instead of solving for output, we're solving for input. We're reversing the places. So we can do this directly, right? I did that with f of x, where I did, f of x equals y, and I solved directly for, if we know what f of x is, f of x equals stuff involving x. I solved it directly for f of x in terms, we had f of x equals x cubed plus 1, and we figured out that it also is the same thing, that the cube root of f of x minus 1 is equal to x, right? We figured that out. So there's this direct way of being able to do this. We can do this directly, but lots of students find this difficult or confusing. So we've got this method of swapping x and y, and also it's just become the standard way to do things, so it's good to practice this way, even though it's not absolutely perfect. It's not a perfect method, but it does the job. As long as you're careful and you pay attention to what you're doing, you closely follow its steps, you will be able to get the answer, you will be able to find the inverse function. Taking inverses can be difficult, right? It seemed a little bit confusing from what I've been saying so far, and it's an easy one to make a mistake on. This means it's really important to check your work. You really want to make sure you check your work on this. How do you do this? Well, remember, by definition, f inverse of f of x is equal to x. That means if we know what f inverse is, we figured out its formula, and we know what f of x is, we were probably told f of x, we can just compose them, right? We know how to compose them from our lesson composite functions. If you didn't check out composite functions, you'll have to watch that before you're able to compose them and do this check. But if it's really the inverse, you'll get x, right? If you compose f inverse with f of x, it has to come out to be x because that's the definition of how we're creating this stuff right from the beginning. Furthermore, we also know f inverse was just f. So it also must be the case that f acting on f inverse of x will give us x as well. So you can compose them in either order when you're doing a check, and you'll wind up being able to get it correct. Let's see a quick example. For example, if f of x equals x cubed plus 1 and f inverse equals cube root of x minus 1, the one we've been working with, how do we check this? Well, let's start off with f inverse of f of x. So we compose this, we plug in f of x is x cubed plus 1, so f inverse acting on x cubed plus 1. Now remember, we're going to plug that into f inverse of x, but it's f inverse of input. Whatever's in the box just goes to the box over here. So it's going to be f inverse will become cube root. Where's the box go? X cubed plus 1. That's our box, minus 1. So cube root of x cubed plus 1 minus 1. Plus 1 minus 1 cancels. Cube root of x cubed equals x. Great. Checks out. What about if we did it the other way? We did it as f of f inverse of x. Hopefully this will work out as well, and it will. So what is f inverse of x? F inverse of x is cube root of x minus 1. So f of cube root of x minus 1. So what is going to happen over here? We know you plug in the box, you plug in the box, right? So f of cube root of x minus 1, we're going to take that and we're going to plug it in right here. So it's going to be cube root of x minus 1, quantity, cubed, because it has to go in as the box, plus 1, finish out that function. Cube root, cube, these are going to cancel each other. We'll get x minus 1 plus 1, which is just equal to x, and it checks out. So we can check it as f inverse of f of x or f of f inverse. Sometimes it might be easier for us to do it one way or the other. We could also do both ways if we want to check and be absolutely doubly sure that we really got our work correct. All right, let's move on to some examples. So using these graphs for assistance, which of the following functions are one-to-one? First one, f of x equals 1 over x. So we do the horizontal line test. It's going to pass at any high horizontal lines. What about as we get lower? Well, we know 1 over x continues to move, right? It never freezes and becomes constant. Does it ever cross this x-axis, though? No, it doesn't. We haven't formally talked about asymptotes yet. We will talk about asymptotes in a later lesson. But 1 over x, as we go positive, right? F of positive. Well, 1 over positive is going to also have to be positive, so it never crosses the x-axis. Same thing goes with the negatives. F of a negative is going to be a negative, so when it goes to the left, it never manages to cross this x-axis. As it goes to the right, it never manages to cross this x-axis, and it keeps changing, so the two things never cross over each other. So yes, this is 1-to-1. What about the blue one? G of x equals x cubed minus 2x squared minus x plus 1. Easy to say, it fails, right? We cross lots of places in the middle here, and it's able to have multiple points at the same time, right? So any one of these, it hits here and here and here. There are 3 points that all give the same output of 0, so it fails the horizontal line test. It is not 1-to-1. Finally, 2x minus 1, x squared plus 1. So 2x minus 1, that's just a line that's going to keep going on this way forever and ever, right? 2x minus 1 when x is less than or equal to 1. This is from piecewise functions. If you haven't checked out piecewise functions, this might be a little confusing, but hopefully you've watched that lesson already. 2x minus 1 as x is less than or equal to negative 1. It's just going to keep going on down and down and down to the left and left and left. And x squared plus 1, it's the right side of the parabola, right? If we plug in higher and higher numbers, it just keeps curving up and up and up to the right. So that means that we're never going to cross. The parabola is never going to double back and manage to touch itself again, right? The parabola might eventually do this, but that part isn't on it. And the line is never going to be able to go down to get and, have itself cross horizontally. So if we do any horizontal line crossing on this, right, it's never going to hit twice, so it is 1-to-1. One thing I'd like to make a special comment on, notice that right here, there's an empty space. There's this gap where it jumps. Is that a problem for a horizontal line test? No, it's not a problem at all because the horizontal line test is allowed to hit no points as well. It's allowed to hit 1 point or 0 points. So in this case, if it goes through that gap, it hits no points, but that's okay. We're only worried about having multiple inputs for the same output. It's okay if there are no inputs to make an output. The important thing that there are no double sets of inputs that all make the same output. Like in the blue one, where we had multiple different places where we could plug in some number, plug in different numbers, but they would all produce zeros. All right, let's actually find an f inverse. F of x equals negative 3x over x plus 3. They told us right from the beginning that it's 1 to 1, so we can jump right to figuring it out. What is f inverse of x? And then after it, we need to check our answer. Okay, so what is f inverse of x? Remember, all of our steps, one by one, f of x equals negative 3x over x plus 3. They told us right from the beginning it's 1 to 1, so we're already checked out. We've already checked out the first one. So next step is we swap y for f of x. Y equals negative 3x over x plus 3. Now that's not the important part of when we reverse, though. We reverse into inverse world. So here is when we go into inverse world, right? We swap, we reverse the place of x and y. So now it is x where y was, and it is negative 3y over y plus 3. Now we just go about this and we solve it for y like we normally would. Multiply both sides by y, we get x times y plus 3 equals negative 3y. Let's distribute this out, xy plus 3x. Let's also move the 3y over, so plus 3y equals 0. Okay? At this point, we'll pull out the y's from these two things. So we'll move them together so we can see it a little bit easier first. Xy plus 3y plus 3x equals 0. Let's subtract that 3x to move it over. Minus 3x here. So then we'll pull out the y's to the right. So we've got x plus 3 times quantity y equals negative 3x. Finally, we divide by that x plus 3, and we get y equals negative 3x over x plus 3. And now finally, we can plug in f inverse for this y. So we plug in and we get f inverse of x is equal to negative 3x over x plus 3. Great. Now let's check and make sure that we got this right. We check this, check it in red. So here's our check. Let's check it by plugging f inverse by plugging f into f inverse. So we want this to come out to be x, right? Should be x if we got everything right. So f inverse of f of x. What is f of x? F of x is this. And here's something funny to notice. Notice negative 3x over x plus 3, negative 3x over x plus 3. Amazingly, it just so happens that for negative 3x over x plus 3, f of x and f inverse of x are the exact same thing. Kind of impressive. We plug this in. We have f inverse. What was f of x? Fx is negative 3x over x plus 3. Now, over here, we plug it in. What's in the box? Box shows up here. Box shows up here. Shows up twice. So it is f inverse on negative 3x over x plus 3 is going to be negative 3. What's in the box? Negative 3x over x plus 3 over negative 3x over x plus 3 plus 3. Great. So first thing that's going to be confusing is we've got this x plus 3 here, and we've got this x plus 3 here. So let's knock that out by multiplying the whole thing by x plus 3 over x plus 3. We can get away with that because it's just the same thing as 1. X plus 3 over x plus 3 is just 1. So x plus 3 over x plus 3. Multiply that here. The x plus 3 will cancel out here, but remember it also has to distribute to the other part because they're not connected through multiplication on that. They're connected through addition. So we've got negative 3x over negative 3x plus 3 times x plus 3. Hey, these two negatives, they cancel out, so we've got 3 times 3x on the top, negative 3x plus 3x plus 3, so we've got 9x on the top divided by negative 3x plus 3x plus 9. Negative 3x plus 3x, they cancel each other out. We've got 9x over 9, 9 over 9, those cancel out, and we've got just x. So checks out. Great, we got the answer. All right, next one. So we've got, this time, a piecewise function. So this is a little confusing. We didn't talk about this formula, but we'll see how to do it. F of x equals negative x plus 1 when x is less than 0, and negative square root of x when x is greater than or equal to 0. So this is confusing, right? We don't know what to do about the different pieces of the piecewise function. We don't know what to do about these two different categories. We've got x less than 0, x greater than or equal to 0. We didn't learn that when we learned how to do inverses, but we could still figure out these two guys, right? We could figure out what is the inverse of negative x plus 1 and what is the inverse of negative root x. We were told explicitly that this is 1-to-1, so we can go ahead and do this, and then we'll think about it. So first, we'll do inverses on these two rules, and then we'll figure out how do they fit together, what are the categories for these two rules. So first off, negative x plus 1, negative x plus 1, we'll have it y equals negative x plus 1. We swap them, so we now hit into our inverse world. So swap their locations, we interchange them, and we are now at, not negative x, the negative does not swap. We are at x equals negative y plus 1. We move the y over, move the x over, we get negative x plus 1. So y equals negative x plus 1, which is going to give us F inverse for at least the first rule here. Now what about the other one? Let's do it as well. So y equals negative root x. We go into inverse mode, we reverse their locations, and we are now at x equals negative root y. So how do we solve for y? Well, we move this negative over, negative x equals root y. Square both sides, we get negative x quantity squared equals y. And then negative x squared, the negatives will cancel out, so we get just x squared equals y. And so this is the inverse rule for this part. Now, here's the part where we start thinking. We know that F inverse is going to break into a piecewise function of using these two different things. Y equals negative x plus 1, so it'll be negative x plus 1 for the first rule, and then x squared for the second rule. But the question is, we don't know what the categories are. So how do we figure out what the categories are? Well, remember, so if f goes from its domain to its range, let's call that a to b, then F inverse does the reverse of that. F inverse goes from B to A. It does the reverse. So what that means is the domain, the thing that determined which rule do we use, we need to do the range to determine which way to get back. So the range on these two rules, so now we're back to using F. So range on F. So range on F for negative x plus 1, well, negative x plus 1 was x less than 0 was the category, so it has to be within those. So what can it go to? Well, if we plug in a really big negative number, like say negative 100, we'll get negative 100 plus 1, so we get 101. So as long as we keep plugging in more and more negative numbers, we get bigger and bigger numbers. So we're able to get all the way out to positive infinity as we're at really far negative numbers. What's the lowest that we can get to? Well, we can get really close to 1, right? As we plug in negative 0.000001, we're really close to being to 1. So we can get right up to 1, but we can't actually touch it. We have to exclude it, so we use parentheses. So the range for the first rule is this. Negative x plus 1 becomes this guy. So I'll put a red dot on that because that matches to this rule here. Now what about the range for the other rule? The range on this rule, negative root x, it's got x is greater than or equal to 0 is its domain. Well, what is the numbers that we can get out of this? What's the largest number we can get out of it? The largest number we can get out of it is actually 0. Why? Because when we plug in any reasonably large positive number, like say 100, the negative square root of 100, negative square root of 100 is negative 10. So as we get bigger and bigger numbers that we plug in, bigger and bigger positive numbers that we plug in, we actually get more and more negative. So we can actually go to any negative number we want. So we can go all the way down to negative infinity. Can we actually reach 0? Yeah, we actually can reach 0 because it is greater than or equal to. So if we plug in x equals 0, we get negative square root of 0, which is just 0, and we put a bracket to indicate that we're actually allowed to do it. So this is the range for negative root x, that rule. It's going to get a green dot on it because it matches to the green rule. So that means negative x plus 1, it's allowed to take in what values? It's allowed to take in the range values. It's allowed to do a reverse on anything that shows up in the range 1, infinity. Also, notice these two ranges, 1, infinity and negative infinity, 0, they don't have any intersection. They don't overlap at all. So we don't have any worries about pulling from one versus pulling from the other. They'll never get in each other's way. So for this one, negative x plus 1, if it's allowed to go from 1 to infinity, then that means we can plug in anything into f inverse where x is greater than 1. X greater than 1, which is to say input. It's not the same x that was up here. It's now just saying placeholder, anything that we're plugging in. What about x squared? Well, that was the green dot. That was allowed to go from negative infinity up to 0, so it's allowed to have x less than or equal to 0. It's allowed to go all the way out to negative infinity, but it can only just get to touching 0. It's allowed to actually have 0, though. X greater than 1, not actually allowed to touch 1, but able to get as close as it wants. And there is our piecewise inverse function. A little bit difficult, but if you think about it, you do each of the inverses, and then you think about how do I get the domain for the inverse? I get it from the domain of f becomes the range of our inverse, and the range of our f becomes the domain of our inverse. So what the original function is able to output to is what the inverse is allowed to take in, and that's how we figured out these rules, these categories, what the categories were for these two different transformations. All right, final example. F and g are one-to-one functions. Now prove that f composed with g inverse is equal to g inverse composed with f inverse. So this might be a little daunting at first. These are weird symbols. We're not used to using these sorts of things. So if that's the case, let's remind ourselves from composition, f composed with g acting on x is equal to f of g of x. Now, I said before, it makes things always easier to see it in that format. So what we want to show is we want to show that g inverse composed with f inverse would be g inverse composed with f inverse, g inverse on f inverse on x. So we want to show that this guy here is an inverse to that guy over there. That's what we're trying to prove, that f composed with g inverse, we know by the definition of how this symbol works, by how inverse f composed with g inverse acting on f composed with g is going on x is going to just leave us with as if we'd done nothing, because we're putting an inverse on something. So we want to show that this means the exact same thing as this right here. So let's just try it out. So we'll set it up like this. F composed with g inverse acting on f composed with g acting on x. Okay, so what does that become? Well, we know that f composed with g acting on x is the same thing as f of g of x. All right, what is f composed with g inverse? Well, we know from over here what we did here that we can break that into g inverse acting on f inverse acting on whatever's going into it. What's going into it here? What's going into it here is this whole thing, right? So it's going to be g inverse acting on f inverse acting on f acting on g acting on x. And then we close up all of those parentheses. So that's a little bit confusing. But hey, we're seeing inverses right next to function, right? F inverse acting on f acting on whatever the heck is in there just cancels out and gets us right back to what we originally had in there. So f inverse acting on f, that cancels out, and we get g inverse acting on whatever was in there, which was g of x. So g inverse acting on g of x, exact same thing. We get down to x. So hey, we've proved it. G inverse composed with F inverse is how we create F composed with G inverse. Great, we've proved it. All right, hope you've got a much better idea of how inverses work at this point. They can be a little bit confusing, but you've got that method to be able to guide you through it. Just follow it really carefully, step by step. The danger is if you break from those steps and do something else, that's where you can make mistakes. If you really understand what's going on, you don't even have to use that method, but it really is the standard method, so it's a good idea to stick with it just because it's what a lot of other people are used to using, and you can find it in a lot of textbooks. All right, we'll see you at educator.com later. Bye.